Thank you. Thanks for the introduction, and thanks to the organizers for inviting me to this wonderful workshop. So there have been already some talks about quantum information-like topics. So my talk is purely in quantum information. And there were like several points of view on tensors. I'm going to bring a new one to the table to make things even more confusing, but hopefully we can discuss about it. And let me just say that this is joint work with Rene, Matthias, Dmitry, Maris, Denis, and Patrick. So this is joint on this is already on the arXiv, so you can have a look at the details. So let me first I will maybe start by explaining the words in the title. So let me start with states. So what I mean by states. So quantum states. So we have already seen this notion of quantum states. So these are just some vector in a tensor product. And to make things confusing, I will swap d and n. So for me, n will be the number of quantum systems, the number of particles, if you want. And d will be the dimension of the local spaces.
You also swap the meaning of the word dimension, right?
No.
Looks fun to me.
It doesn't matter. I like the meaning, but that's
So I think people used up to now the other way around. So n was the dimension of the v, and d was the degree.
This is fine. They were wrong. The notation is consistent. It's all good. Physicists like you.
Physicists like this? Okay. So there are some people. Okay, good. So basically these VIs will be just CD. Okay, so these are actually what are called pure quantum states. And we want these vectors to be of norm 1, like to normalize these tensors. And we draw them, I mean, we will draw these guys as a box with n legs coming out of it. Okay? So, but my talk will be about a more general notion of states. I will talk about density matrices. So let me tell you what density matrices are. But to do this, let me give you some examples. So if I take n equals d equals 2, so 2 qubits. One example, I can take x to be E1 tensor E1. So we draw this guy like this, because we like to call E1 the 0 ket and E2 1 ket. And another example that we have seen is this other state, which was called the unitensor, and in physics is called the maximally entangled state. And this guy, we draw it like this. So x is 1 over square root of 2. This diagram, and the point of this wire is to say that the index here has to be, the two indices have to be equal. So, okay, so this was previously maybe denoted by 2, but I have to normalize it. Denoted like this. And I will call it ket omega. It's maximally entangled state. And in general, I mean, I will denote omega 1 over square root of d sum of EI. Okay. Good. So these are all pure states. Now let me tell you about this more general notion of density matrices. Or mixed quantum states. So this is a generalization of this notion of pure states. And why do we want to generalize this notion? Is because sometimes our system of interest is coupled to a much larger system called the environment. I mean, and you're only interested in what happens with a small number of these qubits, if you want. So the idea is like this: we have this pure state X. It has many legs, but actually we only care about, let's say, 2 of them. This is our system of interest, whereas the other ones are called the environment. And it turns out that we can actually only interact with these 2 out of n systems. So for instance, if you want to measure something, measure an observable A on the system, quantum mechanics tells us, so the Born rule, the quantum mechanic, tells us that the expected value is the scalar product between X and my observable A on the system, tensor the identity on the environment, X. So the picture is something like this. I have X. I have my system qubits here and the other guys on the environment. Here I have my observable A, and I have this other copy of X. Let me note by X bar. And here I'm just putting the identity here. So what I want to do, I just want to talk about what happens on this observable A. And this picture, you can see that this is the same picture as the following one. So here I'll have this picture here. So the one, this was X, this was X bar. Here I have to trace this. Okay. So I'm only concerned about what happens here, and this, I'd like to write it like A rho. And you see, if I only care, or if I only am able to measure observables on 2 out of the n qubits, these observables A, all the information that I will get is actually contained in this object rho, which is this guy here. Yeah, I should have, yeah, let me not draw it like this because it's confusing. All the information is contained in this object rho, which is, so rho. So this is the identity on the system, tensor the trace of the environment, applied to this XX object. So this is the orthogonal projection on X, okay, which lives on my n qubits, and I'm tracing out all of them except the 2 ones that I'm interested in. Okay, so this rho again is X, X bar, and I'm tracing out everything except the first 2 qubits that I'm interested in. Okay, so this rho guy belongs to it's a matrix acting on V1 tensor V2. I'm only considering the first two legs. If you like, this is an element of V1 tensor V1 star. Which is the same, is again the same thing as a tensor product of two matrix spaces. Okay? So these are what I call density matrices or mixed quantum states. And you see the difference is that pure states, I have n, a tensor product of n systems. Now I have a tensor product of two n systems. Or tensor product of n matrix spaces. Here n is 2. Okay, but the nice thing about this new states row is that they, so the set of density matrices I will call it D. Here I have just two spaces, V1 tensor V2. So these are all these matrices row, which are positive semidefinite and trace row equals 1. And what is important here is this positive semidefinite condition. So positive semidefinite. This comes from the fact that I have an orthogonal projection here. I'm taking this partial trace, so what I end up with is the positive semidefinite matrix. And it's this notion here which will be crucial in my talks.
This is Stainsprings. This is Stainsprings theorem, right?
This is, so, yes, so, I mean, the fact that this is positive semidefinite follows from the fact that this is positive semidefinite and I'm putting here a completely positive map. And vice versa, any matrix like this, any positive semidefinite trace 1 matrix can be obtained like this, and this is a very simple version of Stainsprings.
Very simple version of what?
Of Stainsprings theorem.
Oh.
Stainsprings dilation.
It's in quantum physics it's called purification. So any density matrix you can purify it. Actually, if you have two legs here, it's enough to use two legs on the environment. You can build out an artificial environment of two legs such that you can get this. Good. So now tensor series of norm 1. This was a variety. I mean, I have some polynomial equations which give me these the set of pure states. Here, this is a much nicer set because this is a convex set. Its extremal points are very nice. These are rank 1 projections. And the way you should think about the set of density matrices, you should think about it as a quantum version or a non-commutative version of a probability simplex. Because you see, I mean, these density matrices are positive semidefinite trace 1. So you can think about the eigenvalues of rho are non-negative numbers which sum up to 1. So if my matrix rho is diagonal, I just get the probability simplex. If I intersect this set with diagonal matrices, I just get the probability simplex, but I have non-diagonal matrices. So D looks something like a probability simplex, but with rounded corners. I mean, this is the picture that I like to draw. And rounded corner means that I have infinitely many extremal points. These rank 1 projections, whereas in probability simplex I have finitely many extremal points. And when dimension is 2, this d of C2 is actually the unit ball. This is the unit ball in R3, and this is called the Bloch. And the extremal points of the sphere are precisely those rank 1 projections, those pure states. Okay, so this was my crash course on density matrices. It's a more general notion than pure states, which are just tensors of norm 1. Here you can see this as a kind of convexifying this set of norm 1 tensors. But now I want to talk about entanglement. That's the main topic. So to entanglement. So for pure states, X was separable. I've already seen this. If means that X has rank 1. This means that X, I can write it as X1 tensor X2. Xn. This is this rank 1 tensors are the separable tensors, and entangled pure states are the ones which are not like this, so rank 2 or larger. Now for mixed states, the set of separable states is the convex hull of states like this. So let me take here n equals 2. So convex hull of states of the form rho 1 tensor rho 2, where rho I is a density matrix. Okay. So, you know, any state, if I take a quantum state rho 1, 2, this is just a matrix, a positive semi-definite matrix of trace 1. So any state like this can be decomposed as sum of AI tensor BI, because these things span the whole set of matrices. So I can decompose any density matrix like this. However, the question of separability is whether I can find such a decomposition with AI and BI positive semi-definite. So separability for mixed states is about finding a decomposition of a positive semi-definite state as sum of tensor products of positive semi-definite matrices. So here I want, for separability, we want AI and BI positive semi-definite. That's the main. So the question is, do I have a local certificate for the positive semi-definiteness of rho 1, 2 with positive semi-definite matrices? Whereas here, the question for pure states is a question about the rank. Here is a question about positivity. This is the maybe the first message that I want to pass is that for mixed states, separability versus entanglement is a question about positivity, whereas for pure states, a question about the rank.
The A and B, AI and BI are what?
These are matrices. So let me say it again. Any matrix like that, any matrix in the set can be decomposed like this, because matrices, tensor product of matrices span the whole set. But if I ask, moreover, that that all the AIs and the BIs are positive semi-definite, I get a more restrictive notion, and this is the notion of separability. Okay. So now, if I give you a tensor and if I ask you if it has rank 1, it's an easy question. You know, you have your n tensor factors, you split them n minus 1 in the last one, you check if the matrix that you get like this has rank 1. If it does not, then you say no, it doesn't have rank 1, and you continue like this. And so deciding whether a given a tensor that I give you has rank 1 or not, it's an easy question. On the contrary, deciding whether a given rho 1, 2 is, let me call it rho AB, 1, 2, is a separable state, is an NP hard problem. Meaning that there's probably no algorithm which will tell you whether or not a given state is inseparable, is in the subset or not. So it's a hard question. So we have criteria for entanglement, which will just tell you, give you a partial answer to this question. Here is one of them. It starts from the following observation. If I have a separable state, then by rho 1, 2, I can decompose it as a sum of tensor product of positive semi-definite matrices. So if I decide to take a transposition on this second factor, let me write it down. So I act with the identity on the first tensor factor, with the transposition on the second one. Then what I get is I get sum of alpha I tensor beta I transpose, where the transpose is only on the beta part, on the second part. And this will be again a positive semi-definite matrix because this guy was positive semi-definite, beta I was positive semi-definite, its transpose also is positive semi-definite. So this will be positive semi-definite. This is called the partial transposition because it only acts on the second factor. And it's noted by gamma because gamma is half of the t. It's like the second half of the t. It's a very nice notation. And this was kind of the first thing that people tried. I mean, and this is the first thing that you should try. So if someone gives you a quantum state, a bipartite quantum state rho 1, 2, and asks you if it's separable or not, you should try this criterion. You compute its partial transposition. It's a linear operation. And then you check if it's a positive semi-definite matrix. If it's not, then for sure your state was entangled. If it is, you don't know. But so this is, we cannot hope for more, given that the problem is NP-hard. So, example, take rho 1, 2 to be the state omega, which is this rank 1 projection on the maximally entangled state. So remember, this guy here was 1 over square root of 2 E1 plus E2, E2. So what is the rank 1 projection on this vector? So this omega lives in C2 tensor C2. So this is a 4 by 4 matrix now. So this is 1/2. It has ones in the corners. Because this vector here, it's 1 over square root of 2, 1, 0, 0, 1, if you order the basis of the tensor product in a canonical way. So this is my state rho 1, 2. What is the partial transposition of rho 1, 2? So partial transposition means that I'm just going to transpose the blocks and keep the blocks in place. So this guy stays the same because the transpose is the same. Here the one moves here. Here the one moves up. And this guy stays the same. And now you see that this resulting matrix is not positive semi-definite anymore because of the central block here. It's a direct sum. And the central block, it's not positive semi-definite, it has 0 trace. Okay, so this is not. So this means that this omega is entangled. Call it the maximal entangled state. And this makes sense because we started with a pure state, and for pure state, this guy is separable if and only if the vector here has rank 1 and this has rank 2. So no surprise here. Just to show you that this criterion is very easy to check in practice. I mean, you have your density matrix, you permute some entries, you diagonalize your matrix, and you check the spectrum, whether the spectrum is positive. So it's easy. Good. Questions so far?
So the same strategy would work for any map that is positive but not completely positive, right?
That's correct. So this is one way of detecting entanglement, is choosing a map which is positive but not completely positive and acting with this map on half of your system. And since it's not completely positive, you have a chance of seeing a negative eigenvalue. So then you can conclude that the map is, that the state was entangled. Actually, this is a if and only if criterion for small dimensions, where when the total dimension of this thing is less or equal than 6, it's a if and only if. So the state is separable if and only if its partial transpose is positive semidefinite. It has to do with the structure of positive maps. It's a story for another. Yes, because if I put the transposition on the other factor, so if I do the other gamma, this is my preferred gamma, everything transposed. So they have the same spectrum. You can think of, okay, so this is, let me write it down, maybe this is important, maybe this is interesting. So it's a theorem, this is a big theorem. Voronovich had some role to play in this. So rho is separable. So if dim so it's an if and only if the partial transpose is equivalent, positive is equivalent to separability only for dimensions more than 6. For dimensions larger than 6, it's wrong. So you have states which have positive semidefinite partial transpose, but nonetheless are entangled. So this criterion is not powerful enough to detect entanglement. And as Dima suggested, you can say, okay, but you just looked at one map, the transpose. Take more maps, take other positive maps. If you take them all, it's an if and only if statement, but if you take finitely many, you are pretty far from detecting separability. So there are results in this sense. I mean, it's the situation is quite bad, and this was to be expected because the problem is NP hard for large dimensions. So. Good. Now let me tell you about monogamy. What does this mean? So this is a very nice concept. And the idea is as follows. The question is as follows. You have 3 parties, so n equals 3 now. You have 3 parties, Alice, Bob, and Charlie. And the question is, does there exist a state, a quantum state over these 3 parties, such that when I restrict to Alice and Bob, I see omega, and it's the same thing when I restrict to Alice and Charlie. So the question is, can Alice be maximally entangled with Bob and Charlie at the same time? And the answer is no.
Wait, what did it mean to restrict to?
So rho AB, by definition, is identity on A, tensor the identity on B, tensor the trace on C. So if you like pictures, it's like this. So this was observed very early in the physics literature, this phenomenon that Alice cannot be maximally entangled with Bob and Charlie at the same time. So we say that entanglement is a monogamous resource. Why is this? So actually, it's very easy to see that it's very extreme. I mean, the answer is a hard no, in the sense that if rho AB is omega, then the whole state has to be pure. has to be product with Charlie. So this would be omega on Alice and Bob, tensor, some rho Charlie. So it means that if Alice and Bob are maximally entangled, then they can have no other correlation with a third party Charlie. It's a easy, it's a exercise.
I mean, basically, omega AB is rank 1, right? And if there would have been correlations, you
would see the rank, different rank, yeah.
Not rank 1.
Good. So I mean, here the point is that again, so Alice cannot be maximally entangled with Bob and Charlie at the same time, and it's very extreme in the sense. And this actually, this motivates the following definition. So let me define something, a set of states called K extendable. So these are the states, bipartite states rho AB, with the property that there exists a state sigma on A and K copies of Bob, such that Alice and ith Bob is the given state for all I in K. Okay. So these are all the states which admit this K extension, meaning that there is a state now on Alice and K Bobs, such that Alice and every Bob look like your original state. So this here means that omega does not belong to X2. It's precisely what this means. So, of course, X1 is everything. And you see the more Ks I add, the smaller, the more constraints I add. So these sets are decreasing. I denote by x infinity their limit. And the theorem is that this is precisely SEP. It's a big theorem. And this is called the DPS hierarchy. Doherty, Parillo, and Spedalieri. Why is it a hierarchy? Why do we call it a hierarchy? Because checking now, if I give you a state rho AB, checking whether it's in xk, it's a semi-definite program. Meaning that I have to check whether such a quantum state exists. So here it's this being a quantum state. So okay, I should write it. This belongs to D of V Alice tensor V Bob K copies. So I have to check whether there exists a positive semi-definite matrix sigma under these linear constraints. So it's a positive semi-definite program. It's a slice of the PSD cone, of course. And so it's easy to check whether a given state belongs to, it's easy, sorry. It's a semi-definite program to check whether a given state belongs to xk. And if I take k larger and larger, I will converge to this set of separable states. So it's a hierarchy, meaning that these states are decreasing approximation of the set of separable states. And this means that now, if I give you a state rho onto A and if I ask you it's separable, what will you do? What should you do? You should check whether it belongs to x2, if it has a 2 extension. If it does not have a 2 extension, it's entangled. If it has a 2 extension, you should check if it has a 3 extension, etc. If the state is entangled, at some point at k equals 700, it will fail. You will have a certificate that your state is entangled. See, the problem is that the size of these semi-definite programs is exponential in k, so it becomes more and more time-consuming to check these extensions. But kind of this gives you like a very nice answer to this problem of separability.
So is the thing is not in X2 in some sense? Is this a measure of entanglement, a numerical?
Very good question. I wasn't planning to, but now I can tell it to answer it. So there is a more quantitative version, meaning that if I check up to level 5, I have some guarantee that I'm not too far from being separable. So it goes like this. For d squared over k. So as k grows, I'm getting closer and closer to the set of separable states. So this gives you a measure of how good this xk approximates sep. This was your question, right? Good. Okay. So now let me give you the main definition. So in our work, I mean, we have a definition and a result. Maybe both are important. So the definition is quite nice. And the idea is kind of to generalize this notion of extendability. So here it is definition. So main definition. So the definition has two ingredients. It has a graph. And the other ingredient is rho. So it's a bipartite state, density matrix. Symmetric state. So I will use the word symmetric a lot from now on. So here, by symmetric, I mean that that if you want this is the same thing as saying that f commutes with the flip. So f, this is the flip operator. It's a unitary matrix of size d squared, which does what it says. It takes x tensor y, and it gives you y tensor x. Its picture is it's the same as the swap. Sometimes it's called the swap. This is the flip, also known as the swap. Okay. So this rho, I mean, Alice, if you think about Alice and Bob sharing the particles, it means that rho AB is equal to rho BA. It's symmetric in this sense. So these are my two ingredients, the G and the rho. So we say that rho is G extendable if there exists a quantum state sigma. So this will be a density matrix on this CD. So this is my local space. Tensor, how many vertices are in my graph?
So is this the same as rho being a density operator on sim2 of CD?
No.
It looks a little different.
It is.
That would just be f rho equals rho, right?
Exactly. So for instance, the antisymmetric, the projection on the antisymmetric space doesn't live on the symmetric space.
Right.
However, it satisfies this. So I think this is called symmetric, and in the physics literature, the one you said, supported on the symmetric subspace, is called Bose symmetric. Bose like the Indian guy. Yeah. But there are kind of relations. So if you have if you have something like this, you can dilate it to something which is supported on the symmetric space of a larger thing. The two are very connected. So, so what is the definition? So this is the definition. Rho is G extendable. If I can find a sigma which lives not on 2 copies of CD, but on how many vertices there are in my graph copies of CD, such that for all edge in my graph, sigma E is equal to rho. So I pick an edge in my graph. It has 2 incident vertices. Sigma E is sigma restricted to these 2 vertices. So I take the partial trace over all the other vertices. And I want to get my state. So take a moment to look at this definition while I erase the board.
What's the point of the graph?
Well, it's not everything is connected.
Oh,
Well,
the edges.
I mean, I only asked this for edges, right?
So that definition corresponds to the graph where you have 1 point connected to n minus 1.
Exactly, exactly. Exactly. That was my, I was trying to probe if the audience is listening, but it's proactive. The audience is proactive. So this xk, okay, let me call it x, okay. Yeah, xk is precisely the set of this graph, which is the complete graph, the bipartite complete graph with 1 and k vertices. Okay. So basically, we generalize that very important notion of extendability. So second question for the audience. What other graphs should I look at? What are other graphs that should be interesting? Good, let's see. Let me show you what is in every of them. So if rho, so this guy is in every one. Sep, I have to put alpha I tensor beta I. And here I can do it because, you see, I can take alpha I tensor beta I k. But here I have this kind of bipartite. This is why I like to write it like this. But in any case, this is something that is in all of them. So what is the worst case? What is the worst G? The worst G is the G where I have the most requirements. So from now on, I will take G equals Kn. Complete graph. Okay. And I should finish in 7 minutes?
7 minutes.
Okay, good, thanks. Good. So I will focus on this question now. So, so now rho is Kn extendable if, let me write it down explicitly, there is this sigma A1 AN, such that for all I different than j, sigma AI AJ is my given rho. You see, for instance, things like this will work because I will just take sigma sum of alpha I tensor n. Now, there is a theorem which is very useful in quantum information theory, also in many applications in cryptography, which is called the quantum de Finetti theorem. Which says that rho is Kn extendable for all n, if and only if rho is like this. So if I ask my state to be n extendable for all these complete graphs, then I get these kind of this nice subset. Again, there is stuff like this. There are like bounds. But let me get the main result now. 5. So the main result, I mean, what I want to tell you now is I want to give you a state, and I want to answer the question whether the state is Kn extendable. Of course, again, you can do this. This is just a semi-definite program, but the size of the program increases exponentially with n. So we'd like to answer this question for some nice families of states, and this is why we look at symmetric states. And now the word symmetric will mean something else. So this is symmetric 2, maybe. This was symmetric 1. So what do I call a symmetric state now? So let me give you an example of, I will look at the 3 families of symmetric states. Family A are the so-called Werner states. So Reinhard Werner introduced them and popularized them. So these are the states rho. Again, D of CD tensor CD, bipartite state, which is symmetric in the sense that rho commutes with U tensor U. For all unitary U of size D. So this means that U tensor U, rho U tensor U, rho. Okay? So what are these states? Turns out that this condition holds if and only if rho belongs to the span, the subspace of dimension 2, this span of the identity and the flip operator that we have seen. So this is a consequence of Schur-Weil duality. I will not go into this, but we can characterize these states. Basically, if you add this trace 1 condition, you have only one free parameter. And
So you're just asking the trivial representation intersect the density operators, the isotropic
yes,
of the trivial.
yes,
In V1 tensor V1 star tensor V2 tensor V2 star. Yeah. Okay.
but remember that this object has 4 legs. So I have 4 copies. I mean, 2 copies of U and 2 copies of U bar, if you like to. Good. So if you want to write, so this rho, basically, it will be just a convex combination of the antisymmetric, the projection on the antisymmetric space normalized. Okay, let me call it T. Too many P's. T belongs T between 0 and 1. So these are the only density matrices which satisfy this invariance.
It's funny you write D choose 2 but not G plus 1.
Yeah, because D plus 1 doesn't exist, only D exists. I mean, D is the dimension of the space. No, I'm joking. I mean, yeah.
It's really D square minus D choose 2 other.
Yes, that's good. Yes,
That's how you should think about it.
Thank you, Norbert. I like this.
That's even worse.
Good point. Good. So the second ones are the same thing with a twist. Now I'm looking at U tensor U bar. So same story as before. Now I put a bar. If you think about the 4 legs, I mean, I will have still 2 U's and 2 U bars, but in different positions. And now, states like this are of the form T omega. This was the maximally entangled state that I mentioned all the time, plus 1 minus t normalized identity. So t can be a little bit negative. I don't know, minus a little bit. Okay, let me tell you just 0, 1. It can be made a little bit negative, but it's not important. So now this is very nice because this is the class that I'm mostly interested. Why is that? Because now I have a mixture between something which is maximally entangled and something which is separable, in the sense that this is I over d, tensor I over d. So now I can ask the question for which values of t this guy would be Kn extendable. And of course, the more I increase t, n, the more I ask of this extendability, the lower this t should be, the lower the entanglement in the state allowed should be. So I can see how this evolved, and I can also check for the usual extendability, and I can compare the two values and see how this extra symmetry imposed affects the thing. And the final class that we can consider is the same. So this is for all u in ud. And now I can only do orthogonal matrices. And now rho is going to be again a convex mixture. I have omega. I have the antisymmetric guy. And so omega is symmetric, so what's left is p symmetric minus omega divided by d squared minus d choose 2 minus 1. So these are states which are invariant with respect to this. These are called isotropic states. And these are called Brauer states. I think we call them Brauer states because of sure-Weil duality for this orthogonal group. Here we have permutations, here we have this Brauer algebra, so it's called them Brauer states. Yes, so I'm already over time. So let me write a formula and then I will stop. So basically we can answer this question of a Kn extendable. Let me call this rho isotropic sub t. Rho isotropic sub t is Kn extendable if and only if t is smaller than, well, something, 1 over n minus 1, n is odd, or minimum 2d plus 1 over 2d n plus 1, 1 over n minus 1. So if d is larger than n, or d is even, or n is even. So the main result of our paper is that we can say when this thing is Kn extendable. For these three families of highly symmetric states, and we have similar formulas for the other two families. Then there is a whole analysis of comparing this value here with the value that you get for this graph, not the complete graph, but the star graph, and trying to say something about the physics of it, but I'm out of time, so I'll stop here.